So my name is Allan Jude. I've been a FreeBSD server admin for about 13 years now, and I'm also a FreeBSD source and documentation committer. Mostly focused on ZFS, Beehive, UCL, libzo, and other operations-focused type of things. I'm the co-author of FreeBSD Mastery ZFS, which is a book about how to use ZFS. And later this year, definitely in time for BSDCon, unless something goes terribly wrong, the FreeBSD Mastery Advanced ZFS book will also be out. And you can get those from zfsbook.com. My day job, I'm an architect of the scale engine CDN, where we do HTTP delivery and video streaming, including the live stream of EuroBSDCon. And mostly I use ZFS to do things on the internet. So I do a lot of work with ZFS, including I helped bundle the ZFS into the FreeBSD installer so that you can get a nice ZFS system straight out of the installer. And so as part of that, I integrated a technology called ZFS Boot Environments, which basically allows you to have multiple different / partitions based on ZFS snapshots and clones. So if you create a snapshot before you upgrade, and your upgrade doesn't go well, you can just reboot and go back to your system being how it was before based on cloning that snapshot. However, ZFS boot environments don't work if you've encrypted your disk. Because in order to boot from an encrypted disk, you needed an unencrypted partition, and that was where the kernel would live. And obviously, if you update your kernel, you couldn't go backwards. And so that was the impetus of why I decided to work on making it possible to boot from an encrypted ZFS or UFS pool without needing this unencrypted partition for your kernel and modules. And so, because it was the only way to make boot environments work. So I'm a very novice C programmer. I've only been doing it about 1.5 years, and I have no real formal training in it. But what I did was modified GBDE boot and GBDE ZFS boot, which are little small bits of C that handle booting the system, and integrated existing code from the GELI or GEOM GELI, which is the disk encryption system created by Allan. And this presentation is basically the story of how that went, because it's fairly entertaining. How do computers even work? So, in order...
How was...
Yes, it's just do computers even work? So in order to understand this, I had to first learn more about how the computer actually boots in the x86 case. Although, in the end, we ended up not bothering with MBR, but it was important to understand it to build this work. So when you first start up the computer, after the BIOS initializes and so on, it reads the first 512 bytes, which is the master boot record, from the disk that's going to boot off of. And that consists of a 446-byte bootstrap program and the little partition table. And we call that first bit of code there boot 0. Or in the source code, it's boot0.s, which is a tiny assembly program. That looks at the partition table and finds which partition is marked as active, then reads the first 512 bytes of that partition, which is the volume boot record.
Good question. Yes. This is 32-bit code at this point?
No.
Oh, this could be 64-bit.
This is 16-bit.
Yes.
So.
Right, extension. Right.
Yeah, so that will become very important soon.
Okay.
Actually, more precisely, it's real mode boot.
Yeah. So the next 512 bytes, which is the volume boot record, which we call boot 1, is responsible for loading boot 2, which in UFS is conveniently stashed in the first 15 sectors of the file system, which the file system purposely doesn't use so that you can stick the boot code back. And then that boot 2 has just enough knowledge of UFS to find the inode number of /boot/loader and read the blocks and execute it. And then once you fire up the loader, this prints out the fancy menu and does all the fourth things, prints the little beastie on the screen, and then that code loads the kernel and the system boots. However, doing that with ZFS gets evil very quickly. So in order to boot ZFS with the master boot record, you have the boot 0 reads a different boot 1, which is stored in the first bit of the partition. But that boot 1 is different, and instead of, because ZFS doesn't have the first 15 sectors available for you to do whatever you want with, like UFS does, ZFS has exactly 64 kilobytes of space available, exactly 1 megabyte into the partition. It's not clear whether that was done on purpose or if it just happened to be a space that in the on-disk format isn't used right now. Importantly, it makes updating this bit of the boot code more complicated because you really don't want to be DBing random things in the middle of your drive while you've mounted that file system. But it's basically similar, except for it reads /boot/ZFS loader. So I was wrong. And then that loader presents a menu and so on. Luckily, this work focuses on GPT, which is a less contrived system. There. So with GPT, instead of the limit of 4 partitions, you can have more, up to 128, and you can actually have partitions that are bigger than 2 terabytes, which is quite helpful when you have 36 6-terabyte disks. But it has, the first 512 bytes of GPT are what's called a protected MBR. It's basically a fake MBR that exposes one really large partition, so that if you boot an older operating system that doesn't understand what GPT is, it doesn't offer to format the disk for you. Because, Windows 95 and so on would do that. You'd be like, oh, that disk is not formatted. Let me just format that 32 for you. Yeah. So that little 512 bytes is a little assembly program written by John Baldwin called PMBR. And it basically looks at the GPT partition table and finds the partition with the type FreeBSD-boot and reads the code that's in there and executes it. That's how it finds boot 1 and boot 2. And it reads up to 545 kilobytes, which is a very random number, and I'm not sure why that was selected, but that's what it is.
It's like because it was just the smallest number that could be fit, because that space is very, very tight for the GBD loader.
And so in that FreeBSD-boot partition, you would either put GBD boot if you're using UFS, or GBD ZFS boot if you're using ZFS. And this, those two files are basically concatenations of boot 1, which is a bit more assembly, and boot 2, which is a C program compiled. And the first part of that, the GBD LDR, would then relocate the boot 2 code from where the PMBR loaded it to the right spot, and then jump to it and execute it. And then once either of those boot 2 fires up, it would load the loader or the boot ZFS loader, depending if it was UFS or ZFS. So to get started with this, almost a year ago, when I started on this, I decided it would make sense to make a GBD-GELI boot as an option, and to try to make a single boot code that would boot UFS or ZFS if it was encrypted. Which is still a good idea, but was abandoned because it was more work than I felt like doing at the time. In particular, the question was, if you have a system that has both a UFS and a ZFS partition, how do you decide which one to boot? Because GBD doesn't really have an active flag like other, like MBR, so it's a, which one has a, I think there's a boot me flag. That's FreeBSD specific, that's not actually standard. So instead, I went back to implementing GELI directly in each of those 2 separate boot codes. Although I purposely didn't touch the ZFS boot version for MBR, mostly because it is constrained to that 64 kilobytes of available space in the ZFS label, and so it could never, the code would end up being too big and it would never fit. But of course, working with the boot code is hard. As I started programming, first of all, being a junior programmer, I have no idea what I'm doing. And in the boot code, you can't just run a debugger against it, and when it breaks, it usually either just hangs or crashes VirtualBox. That was it. And it's really hard to work with, right? And you don't get a seg fault in a core node that you can go back and look at. So the basic model of how to boot from an encrypted drive was first have to figure out, is the partition encrypted? And so, like all of the GEOM providers, GELI uses the very last sector of the provider to store metadata. And so we read the very last sector of the disk and look for the magic string GEOM : ELI, and that lets us know that it's GELI encrypted rather than something else. Even this wasn't that straightforward, because in the boot code we have this struct dsk, which tells us about the partitions and so on, but it has both a length and an offset, but it also has a start member that in some cases, like I think the ZFS boot code, start points to the beginning of the partition, and so the length and the offset are all relative to that start, but in the ZFS code it doesn't use it, and so you have to not subtract it to find the absolute position in the disk to find the same partition. So once I started digging into the code for ZFS, how ZFS actually boots, I was happily surprised that ZFS doesn't just read directly from the disk, but uses a callback or a function. You pass the ZFS probe command or function, a pointer to a function that it will use to read from the disk. And so it was quite easy to just replace the function that was being passed to it with one that would GELI decrypt the block of data before it passed it to ZFS. And so I ended up actually rewriting the ways UFS boots to do the same thing, so that either of them could be passed through a function that would GELI decrypt it. So once we figure out that a partition is encrypted, the next thing to do is decrypt it. So first you have to read the metadata, the rest of that very last sector, and in it, it contains things like what algorithm it was encrypted with, whether it has authentication, how big the key is, and an encrypted version of the master key. So to decrypt the master key, we prompt the user for their GELI password, and use that to decrypt the master password. And then you can use an HMAC to verify that the decrypted one is actually correct. So at this point, the boot code doesn't have any crypto, so it can't actually decrypt anything yet. And it turns out that in GELI for the kernel, it uses the kernel's crypto APIs to be able to, not quite asynchronous, but to basically shove a bunch of packets in and say, or blocks in and say decrypt these, and then get notified when they're done. To do that, and that's much too complicated and too big to use in the boot code. So when I first started, I decided the easiest way to work was to find a really small implementation of AES and use that to be able to decrypt. So, doing the typical newbie thing, I just frogged around on GitHub until I found a small AES implementation that has a public domain license. And copy and pasted that into a file that I included in the boot code. The downside was it was AES CBC 128 only. It didn't do 256 or XTS, which is the most common way to encrypt a disk. But at this point, I was just trying to get something working first, and then I'll fix the other problems later. And then I borrowed a bunch of functions I needed from the kernel GELI code to read the metadata and figure out what the encryption type is and so on. In particular, you have to check which version of GELI it's using. There are 7 versions now. And in certain versions, there's one key for the whole pool, And in later versions, the key gets rotated every 200 gigabytes or something. So if you have a larger provider, each chunk is done with a different key that's derived. And so looking at the metadata, you have to set a bunch of flags and switch the way you do the encryption and decryption depending on which version of GELI it is. And then we borrowed the function to decrypt and validate the master key to make sure that the password you typed in was the right one. And calculate the HMAC and the sector key and the initialization vectors. So then the next thing I needed was hashing algorithms. Turns out GELI actually uses all of them. For the metadata, I think it's slightly historical, and because there's only 512 bytes, they use MD5 to verify that the metadata is consistent or hasn't been modified. Then it uses SHA-256 to generate the unpredictable initialization vector that's different for each sector. But it uses SHA-512 for all of the HMACs. So I needed all three of those hashing algorithms. Unlike elsewhere in the boot code where they pound include the actual .c files in order to just make one small blob, that didn't work with SHA-256 and SHA-512 because they defined some macros different with the same name but differently between SHA-256 and SHA-512. There's a bunch of crypto primitives like S and P. They're just completely different between the two algorithms. So just including those two wholesale didn't work. At one point I went through and renamed them all. I was like, this is terrible. Let's not do that. So I had the bright idea to just modify libstan to include those. So I ended up with basically a shared library, a static library that had SHA-256 and SHA-512 so that I could just use them. Although eventually I replaced that and made my own static library because I ended up needing a bunch of things and I didn't want to keep loading libstan for people that weren't going to use the encryption stuff. So then what I thought would be fairly easy, which is to ask the user to type in their password. The first version I did, I borrowed the getStir from the common console code, which lets you prompt for stuff all the time. And then I modified it so instead of echoing back the character you typed, it would echo the asterisk. But it turns out that while that works in boot 2, when the loader starts, it's different because it has to support a serial console. And so it uses a different backing system to actually read a character from the console. And so now I needed two different versions of this function to do that. And it turns out both of them actually contain the same bug, where both getStir and getChar are, you specify a maximum length as well for how much they're going to type. And you can see here, I've shortened the function a bit to see the way they did this. If once you've passed the maximum characters you're allowed to type, it continues to echo more characters instead of not. This appears to actually be unintentional. So I actually went and borrowed better ngetS from libstan, which actually comes from NetBSD, and it doesn't have this problem. But grepping around in the sys boot, there are at least 6 different versions of the getStir with the bug in the boot directory. In the paper, you see that's listed as future work.
Somebody should do something.
Yes.
You should file a PR on that.
Is it a bug though? Is it a bug though?
Yes.
Is it a bug? I mean, it could be.
You're calling a function and saying, give me the characters the user types up to 10 characters. And the user types in 15 characters, and it continues to let them type, even though you've told it to stop after 10.
Right, but couldn't that be a thing to help somebody disguise the length of their password at a prompt?
No, for that, what you would want to do is, what the loader version of this does is instead of printing asterisks, it spins a twiddle to let you know that what you're typing is doing something, but without exposing the length of your password. But I didn't do that because it was too complicated. So in this case, if you're supposed to stop taking input after a length, you kind of want to tell the user that you're ignoring everything they're typing at this point, right? More importantly, looking at the code, it's obvious that with the tabbing, that they meant for that to be included in the if, and it wasn't. So, my expectation going into this, after the amount of work I had done, was that boot 2 would start, taste the partition to see if it's GELI. If it is, it would read the master key, the encrypted master key, prompt the user for the password, use that password to decrypt the master key, and then be ready to decrypt, to come up with the individual unpredictable sector keys and decrypt individual sectors as we try to read them. But instead what happened was I got a triple fault and then VirtualBox crashed. I was like, what is a triple fault anyway? So I took the code and put it on my spare laptop and fired it up on there instead, and it just rebooted in a loop. And I was like, I really don't know where to go from here. So it turns out, when John Baldwin wrote GBDE LDR back in, I think, 2000 something for Yahoo, and because it's written in 16-bit real mode, it copies only the first 64 kilobytes of the boot code into the correct memory location and jumps to it. Because you can't copy more than 64 kilobytes at a time in 16-bit. And so, all of a sudden, when I added encryption, my boot code had grown to about 90 kilobytes. And so, when you only have the first 2/3 of your boot code, you get a triple fault. The 64 kilobyte limit made sense originally because the code to boot UFS was 15 or 16 kilobytes, and even ZFS was only 42. But once you take ZFS and add encryption support, it gets to about 90 kilobytes. And so I was like, well, this can't be that hard to fix, right? So I'll get to the amount of craziness that was involved in fixing that in a minute. But when I determined that I couldn't easily fix that problem, I instead went back to working on UFS, because I just wanted to have something that worked before I spent any more time trying to solve a very difficult problem. So I reworked the UFS boot code to use that same, give me a function that I would use to read from the disk pointer system. And after poking on it for quite a few nights, late into the night, I eventually got decryption to work. This involved a lot of printfs showing me before and after decryption. It's like, I can almost see the right output there. So the GBDE boot code decrypted the file system and loaded bootloader and launched it. I was very pleased with myself. And then the loader immediately failed because it didn't understand GELI encryption yet. And so it's like, I can't find the kernel. All I see is gibberish. There's not even a file system here. What are you doing? So yes, boot code is actually a very restricted environment because you haven't started the kernel yet, so there's no kernel. There's no libc. You don't even get malloc or even panic. You literally have almost nothing. Libstand includes, or because libstand provides a lot of the string manipulation functions, it means if you try to use any code that includes strings.h or string.h, it actually conflicts and breaks everything. So the boot code, instead of having a real malloc, it implements a very simple thing where it takes about 3 megabytes of heap space and just keeps a pointer. You can malloc, but there's no free. Yeah, ideally. Just better hope you don't need any more than 3 megabytes. So in particular, we're trying to avoid making a bunch of small allocations and try to avoid using as much memory as possible. So now that I had got GBDE boot to read the loader and start it, I had to teach the loader how to do GELI. And so I grabbed the code for the loader, and it's like this long and doesn't talk about reading from the disk at all. But eventually, after reading around and following, oh, it calls this function, which calls this function, which calls this function, here. There's in conf.c for the loader, it has a list of supported file systems, and they're pointers to a common set of functions to do common file system operations, like open, close, read, write, etc. And so I was like, well, I could probably make a GELI version of UFS and a GELI version of ZFS, and have those lists and teach you how to do it there. But luckily, eventually I found in libi386 the actual load level routine that does the BIOS calls to actually read from the disk. And I added some code in there to, when you open the disk, it checks if it's GELI, and if it is, it keeps track of that. And then when you read from a disk or a partition that's known to be GELI encrypted, it decrypts the data before returning it up the stack. So ideally, we would actually implement this more transparently in some kind of layered fashion. Thomas Soon, the Illumos developer who's porting the FreeBSD loader to Illumos, has also contributed back a bunch of improvements to our block caching that happens in the loader. And him and I are thinking about some way we could improve the block cache and have a more layered approach where we could easily stick GELI in the middle of that. And maybe other things as well.
But how do you get the users or the decryption?
At this point, when the loader starts, it prompts you again.
Okay.
So you get prompted for your password, you type it in,
Yeah.
and it loads the loader, which then prompts you for your password, you type it in. And when we get slightly past this, the kernel starts, and at malroot, it prompts you for your password.
So you should pick a really short password then to make it easier.
When I was doing this originally, the password was statically defined in the code as test, and it didn't work for anything else because I was having trouble with actually prompting for the password. And once I got that sorted, yeah. There's a second laptop in my bag that has a demo of this working, and the password is test. Because when I was doing this in VirtualBox, I was actually doing a ZFS mirror. So I had 2 disks. So you'd have to type in your password twice at boot 2, twice at the loader, and twice in the kernel. Or not twice in the kernel, but we'll get to that. So anyway, at this point, we've finally successfully booted a GELI encrypted disk, because the loader can now load the kernel. But it only supports AES-CBC 128. It doesn't support ZFS, because we're stuck with this 64 kilobyte limit, and that's not that useful. So in order to get any further, since my real goal was ZFS, UFS was more just a proof of concept that it would work, and for completeness, we had to overcome the 64 kilobyte limit. So I tried a number of different things. First, I told the compiler, optimize for a smaller binary. It didn't make much difference. So I tried a bunch of other things. Turns out optimizing more just made it bigger. So I tried to, so I went into the assembly for the GBDE loader, and it has this little define at the top that says, hey, copy 0x80 blocks, right? So copy 64 blocks, or 64 512 byte blocks. So I just increased that number, like hex 100, which is twice as much. And then the assembly compiler just laughed at me and said, I switched it back to 64 kilobytes because that's the most you can do. So then I was like, well, let's just make this 32-bit, right? You just stick E in front of all the assembly things, right?
Actually, that can be done.
That's what somebody thought when they told me to just try that. But then the CPU just laughed at me. So then I summoned the collective wisdom of the FreeBSD super friends. So I asked Aidan Adler, who is one of my documentation mentors, and he took a look at trying to do the conversion to 32-bit to copy more than 64 kilobyte at a time. And when that wasn't working, he looked at maybe making a copy 2 blocks of 64K. But in no time, everybody's busy and he didn't have much time to continue to work on that. So I asked John Mark Kearney, and he seemed receptive to the idea at first. But once he understood what the problem was and had read the assembly code, he was like, nope. So he was like, you should ask John Baldwin. He wrote the assembly. He'll know how to fix it. So I asked John Baldwin, and he's like, you should find a different way to do that. So he suggested making a new partition that only held the loader or something. That would, so that I could keep the code smaller, not have to have encryption in boot 2, only have to have it in the loader. But didn't really want to do that either. So then at FreeBSDCon, Dexter had told Peter Greeton about my plight, and he was like, oh sure, I can take a look at that. I was very excited. But once he understood what the problem was, he instead taught me how to use QEMU to debug the assembly and try to figure out why, like, single step through the assembly and try to, but I don't actually know assembly, so it wasn't that helpful. It's like just a bunch of numbers going by. Like, I have no idea what's happening, other than it's not working. So my friend Dylan took a couple of cracks at drafting new versions of the assembly code, but he hadn't finished it by the end of the conference, and after that he was back to work every day. Nothing came of it. Then EuroBSDCon in Stockholm last year. During the developer summit, during one of the breaks, Colin Percival came up to me and he says, I've heard you're having this problem. And he's like, 64-bit assembly, I knew this. It was apparently the last assembly he had ever done when he was in school. And so he did a first draft right there at the Dev Summit, but that just caused the BTX client to crash. Then back at the hotel that night in the little hacker lab we had, he gave me a second draft, but that just crashed. And then over each night of EuroBSDCon, he sent me another draft, but it didn't quite work.
Sounds like you're building a castle out of Monty Python skit.
So we all went home, and I was, a little sad. I was like, I'm never going to solve this problem. What can I do? But then, about 2 or 3 days later, Colin pinged me on IRC, and he's like, well, I got this new patch. It only does 64 kilobytes, but it does it in a new way, doing 2 32 kilobyte chunks. And if that works, we can just make a new 4. Good. So we tried that, and oh my, it worked. And then on October 8th, he gave me the final version that copied 4 chunks of 32 kilobytes, and it actually worked, and it booted. Turns out 21 new lines, the 21-line diff to the assembly, and all my problems went away.
Do you understand each of these 21 instructions?
I think one of them, because it's just adding 1. That's about it. So then, at this point, now that space isn't a concern, I'm looking at building something that would actually be acceptable to the FreeBSD project, rather than I copy and pasted something from GitHub. So the first thing I did was borrow the AES implementation out of the crypto subsystem in the kernel, which is the original public domain Rindall thing. But I had to fake define string H, because otherwise it would conflict. It would try to pull in like libc into my loader, and that just exploded. So because libstand is already providing slightly different versions of those functions, if you pull in string.h, its prototypes of those functions don't match up exactly, and the compiler. So I had to pretend that I included string.h to make it happy. And then I wanted to borrow the AES-XCS code from the OpenCrypto framework that's in the kernel. However, the OpenCrypto framework consists of one giant file called xform.c that contains all the transforms for about a dozen types of encryption and 24 hashes and deflate compression just because. So that was not what I wanted and was too big and had too many dependencies. So I copy and pasted out just the AES-XTS bits and put them in a new file in sysboot. And I modified them because it was malloking a new chunk to put the key into, and I gave it a static buffer instead to avoid having to do a malloc there. So once I hooked all these bits together and dealt with all the little nitty problems that were coming up, I could boot UFS or ZFS from 256-bit AES-XTS. And I tested that CBC worked now that I'd switched away from Tiny-AES-C. But at this point, the code was quite an ugly mess of copy and paste and including files from the kernel and so on. Like, including .c files, not .h files. Yeah, well, that's how the rest of the boot code does it. Yeah, so, and it was full of printfs so that I would have some visibility of what the hell was going on. It's like, why is it pausing here for a long time? So, yeah, at that point, instead of copying and pasting the code from the kernel, I switched to trying to include it, but it was still pretty ugly. And the main one was the xform.c was pretty messy because it was too big to just include the whole thing. So when I put this up for review, and it was reviewed by the FreeBSD security officer, they're like, well, if it'll make it better, maybe actually breaking that xform.c and OpenCrypto up into separate files for each algorithm wouldn't be a terrible idea. So they let me do that. And so I went through there and broke up the OpenCrypto framework into a separate file for each different algorithm. So I had the bright idea of using stn copy from xform.c to xform_algorithm.c for each of the 8 or so algorithms, then just deleting the algorithms that didn't match for each file. So the diff that I posted was quite long, but only consisted of deleted lines. And you can see that I hadn't modified any of the actual crypto algorithms. I'm not sure if that actually made it easier to review or not. But yeah, they kept the history, and importantly, it showed that I didn't actually change any of the cryptograms. Because I wanted to make sure I didn't accidentally change one of them and break something. So most of the GELI code had survived unmodified, but had been copy and pasted. So, but one of the big changes I had made is instead of using the big struct this big in GELI that has all of the running state, I had modified the code to just use the on-disk metadata state, because there was mostly the only things I cared about. But when I tried to switch the code to using the unmodified GELI code from the kernel instead of a private copy of it for the bootloader, I had to switch that back. So undoing a bunch of work that I had done trying to make it cleaner. The one big thing I had to do was both the encryption and decryption stuff and the calculation of the HMAX was all in one file. And since I didn't want to use the encryption from GELI because it uses OpenSSL and the kernel's framework, I wanted just to do very basic AES on one block at a time. And I didn't care about using crypto accelerators because it's the boot code. There's no kernel yet, you can't do that. So I got Powell to let me break that up into 2 files so that we could just include the ones we needed. And basically end up pulling all the bits of GELI that we needed into that libGELI boot static library. The only function I had to override was ELI crypto decrypt to make it use the basic AES instead of the kernel framework. And the rest of the code is used unmodified now, which meant for a lot less new code, which was a lot less copy and pasted code. And I had to move some if-defs around in GELI so that stuff that was specific to the kernel wasn't compiled into the loader. And one function was only available in the kernel, but I needed it, so I had to move it outside the if-def. So yes, then we get to password caching. So boot2 prompts you for the password for each of your disks, and then the loader prompts you for the password for each of your disks. However, in the past, Colin Percival had been annoyed by this on his computer, and so he modified GEOM ELI, the kernel module, so that once you've entered your password once, on the second, third, and fourth disk, it tries the password you just used first, but doesn't count it against your 3 tries. And only if that's not the right password does it prompt you for the disk. So it still works if you have 4 different passwords for each of your disks, but allows you to not have to type the same password 4 times to boot your system. So I blatantly stole that concept and applied it to boot2 and loader, so that my ZFS mirror wouldn't require me to type the password 6 times, but only 3 times. The other thing he had done is with Chris Moore and Devin Teskey, when Chris was trying to replace Grub, or make Grub work with GELI, was a way for the loader to pass the password into the kernel. So the main problem with the way GELI worked before was that the password prompt would come up in the middle of your device detection. So if you had a USB device show up kind of late, it would clobber the prompt, you wouldn't see it. I remember Brad and I discovered a bug one time where if you failed the first password, it zeroed the key, and if you tried a second time, even with the right password, it would always say it was wrong, because it zeroed the key. Yeah, so the first prompt was buried in all this demessage stuff. So Brad presses enter, which is not the right password, and then when he gets the prompt, he types the correct password, and it does nothing. It says that's not the right password. Like, I'm damn sure that's the right password. So him and I had some fun finding that one on IRC quite a while ago. So what Chris wanted to do was allow prompt for the password during the loader earlier. So you type the password in there, and then it would just get passed to the kernel, and you wouldn't have to do the prompt in the middle there. So Colin came up with a way where you can set the kernel environment variable in the loader, and then when the ELI kernel module loads, it pulls that into its memory and erases it from the environment and overwrites it so that your password's not just sitting somewhere. So I reused that. So the loader now, once you type your password into the loader, it can pass it into the kernel. So now we're down to 2 password prompts per disk.
So, a question, have you also just double checked that you, after the system is booted up, in a virtual machine that you make, say, a memory dump and correct?
Yes, that's what Colin and Chris did that for their work. They grepped over devmem and made sure the password wasn't in there.
Yeah, okay, but also the KN thing, or?
Right, so the KN would be there. So yes, they make sure that that gets unset and overwritten, overwritten and unset.
For all of the separate steps, they check.
Well, for mine, I haven't actually double checked that, but we do zero them out.
Okay.
I'd love for you to review the code on this on Fabricator.
Okay, well, send me this.
So at this point, now you only have to type in your password twice per disk. Twice total. Once in boot2 and once in the loader. Because the loader will then pass the password into the kernel and save you from typing in that password. So how do I get the data from boot2 to the loader, though? Turns out ZFS, again, has the answer to this. ZFS needs to pass the globally unique ID of the pool from boot2 to the loader. So the loader boots the same pool that you started booting from already. And so it has this ZFS boot args struct that passes. What's really interesting about the way they did this was to make it compatible with different versions, or make it future-proof. The very first member of the struct is a size. That's the size of the struct. And before you read a member, you check that the offset of that member is not greater than the size. So as you add new members, if the boot2 is older and doesn't create, the struct isn't that big then, you don't read out of bounds. You'd be like, okay, the boot2 that passed this in doesn't support passing the password yet, so we'll just ignore it. I found that very interesting as a kind of programming trope. So this way, if you haven't updated your boot code yet, the newer loader isn't going to barf because your boot code's out of sync. So I added a new member to the ZFS boot args that holds the password.
How long? How long?
255 bytes. So after you've typed in the password, when it copies it into this struct, it B0s the version that it had in memory before, and then passes it to the loader, and the loader B0s that out when it passes it into the kernel. And then the GELI kernel module zeroes that out when it uses it to decrypt your disk, and then zeroes it out, and it's gone. And so now you type the password once in boot 2, and it passes it to the loader, which decrypts your disk with it, and passes it to the kernel, which decrypts your disk with it and boots the system. So now you only have to type the password once instead of 6 times.
What do you do if you have 6 disks with 6 different passwords?
Then you have to type them over and over again. What you do is eventually break down and use the same password for all 6 disks.
But security.
But I mean, that only applies to the case if you actually use them from, like the boot from.
Yes. One of the important things is the boot 2 code only attaches to GELI disks that have the boot flag set. So if you have ones that you don't want to decrypt at boot, you just don't set the boot flag, and the bootloader will pretend that they're
So
not.
if you have 6 disks with all of the same password, all of them will be.
If they have the boot flag set. If they don't have the boot flag set, they'll be ignored. So what remains to be done? Currently, GELI boot only supports the user provided, like the user typing in a passphrase. Ideally, we would like to support key files, like on a USB stick. In the paper that was published in the proceedings, I have a couple of ideas about that. After talking to Powell about it at the Storage Summit 3 weeks ago, I think the direction we're leaning is a new partition type, like GELI key or something that would go on a USB stick, and you'd make like a 2 kilobyte or 4 kilobyte partition and just raw right into it the key file.
Would it already make sense that, so if I understand correctly, the crypto that's involved, if you're not using a key file but a passphrase, there is somehow some magic routine that turns that.
It uses PKCS5 and does like 500,000. Well, when you GELI init, it figures out what would take about 2 seconds on your processor and does that many rounds of like KBDF.
Yeah, and then eventually you get like a key that would normally be of the same format.
Yes.
So would it make sense to, instead of passing through a passphrase, which we do right now, already sort of make it future-proof by passing through the key, and then that way, if you want to add support for adding stuff, loading the key from the USB key,
then you wouldn't have to
then you
reread
don't
it.
have to extend the entire pipeline, but just the beginning.
That's a good idea. So yeah, the question there is where to store the key. We're thinking a raw partition type. We're not sure how well USB keys are exposed during like boot 2. So there's no kernel yet. And oftentimes your BIOS will be like, oh, there's a USB key here. Let me try to boot off of it. And that's not necessarily what we want. So still some work to do there to figure out how to support keys in a way that will make sense. I don't know if it's worth trying to support some of the other algorithms that GELI supports, like Flowfish and Camilla. I think most people are on AES XDS at this point because of ASNI means it gives much better performance than anything else. Support for GELI sector authentication, where basically you use a couple extra bytes to check that the sector hasn't been modified. But Powell says he wished he had never even added that, and that you should just use ZFS instead. So probably not worth the effort. Hopefully in time for BSDCon, I will do all this work over again for UEFI. UEFI has modules for the file systems, and I'm hoping that they can be layered in such a way that I can just write GELI once and do it underneath both UFS and ZFS. But we'll have to see how that works. Other stuff, maybe a version 8 of GELI that stops using SHA-256 for anything, but uses SHA-512 truncated to 256. because on 64-bit CPUs, because of the larger word size, it's about 50% faster to calculate the same thing. I don't know. Yes, ZFS has support for that now. I just haven't known. But yeah, so it might be worth switching that up in GELI and seeing if it makes any performance difference. In general, clean up the boot code and more code reuse. There's a lot of duplicated code in sysboot, and like I said, 6 broken copies of getster that I should get around to fixing up. And I'm still very interested in the idea of making one boot code that can do UFS and ZFS. And I don't know, if you have ZFS, it should default to ZFS maybe. Or maybe we use the bootme flag to let you specify which one you want to do. Other people have talked about maybe creating a fuse module for GELI so that you can mount your GELI encrypted disk on other operating systems. Just something when I got digging into the GELI code and saw how it's actually not that complicated, I thought maybe that would be a fun thing to do. But I don't use other operating systems, so it doesn't actually provide anything to me. But an encrypted USB stick that you can also mount in Linux might be interesting. And ZFS book. And each week, Chris Moore and myself do BSD Now.TV, which is a podcast where we interview BSD developers and talk about the latest news and various BSD things. So if you've never watched it, you should check it out. If you've never been interviewed, you should volunteer. So, any questions?
2 questions. First, how about GELI-OS partition instead of GELI sector?
Sorry.
GELI-OS partition, 3 pages.
Right, the sector authentication?
Sorry. Yes, support GELI sector also.
Yes.
Yeah. Instead of GELI-OS partition, GPT partition. So, to clean first GELI partition remove clear. So simply GELI partition is not activate. Just idea. It's just idea.
So yeah, if you have GELI sector turned on, it's just not used. It doesn't trigger anything like that. Warren?
I was just thinking if you have if you want to use a USB key for your
Key file.
or pass, whatever you want to put on there, put a bootloader on it, boot from it. It detects that you have that key file and then boots your other disk.
Yeah.
Because then you've got it all in one place and you don't have to worry about the system picking one device to boot.
Yeah, and also sometimes the BIOS won't expose devices other than the boot device. So yeah, that might be the most sensible way to do it.
More specifically, it will normally not do anything about USB if you don't boot from USB.
Yeah.
And on the other hand, having a small USB stack for use in a second stage bootloader would actually be quite nice if you want to use something like a YubiKey, for example, to store or to do the actual keying, so it would be quite handy to have.
Could you maybe, or is there also some support plan, or have people thought about both combining the key from the class trace you type in, but also using some kind of as called TPM chip thing, where you store the key in, so that when you the disk, say if it's a laptop, but the disk also only works in combination with that specific piece of hardware. Right. Some companies are also interested in those kinds of things.
Yeah, I don't know how you access the TPM without the kernel.
I also have absolutely no idea.
That'd be for someone else to build on top of this, which I'd be happy for them to do.
Is this going to be in FreeBSD 11?
Hopefully this will be committed in the next week or two.
To F?
Yes. So it should be time for 11.
Right.
it slipped its ability to make it in for 10.3. The other bit of work that went along with this was as part of the loader menu having the list of ZFS Boot Environments. But that I managed to get in time for 10.3.
Can you tell me the performance decreasement using the GELI decryption feature?
During the early bits of the boot phase, it's pretty slow because it's software. But once you've booted into the OS and are using it, if you have AES-C on your processor, which is most modern processors now, it's faster than your disk is, so there's actually no performance benefit. Well, not a noticeable performance benefit. With AES-C, easily a gigabyte or 2 per second offload.
So, but I guess also the performance overhead in bootloader is not that.
Right, you're only reading a couple of kilobytes from the encrypted disk, so
yeah, and I seem to remember most of the, I know nothing about PCs, but the largest amount of overhead you always have in bootloader is the actual I/O and BIOS calls and all that kind of stupid stuff, right? The actual, if you're running CPU cycles, that's fast.
Right.
Well, you're actually reading a couple of megabytes with the kernel, but even with sometimes 20 megabytes was a really slow AIS implementation is going to add at most a second to your boot time.
Yeah, exactly.
On x86.
The biggest thing in the boot time currently is the key derivation. So after you type in the passphrase, it does, it derives the key from that.
That would also be sped up then if you would propagate the key instead of the fast.
Yes, you would have to do it the second time. So
Yeah.
you see, doing it the first time here takes a while. Then it loads the loader, and then it does it a second time. So if we pass the already derived key, that would avoid that. Also, you can, when you do the GELI init, if you're worried about the amount of time it takes to boot up, you can specify lower iterations. On this machine, when you do the GELI init, it basically times how long it takes to do it, and aims for about 2 seconds worth on your CPU as the target time. But it's slower in the BIOS because it's not multi-core.
Oh yeah, and that gets stored on the disk so the bootloader knows how many iterations.
Yes. Then the number of iterations is stored in the metadata. So you can, during GELI init, you can specifically say, I want the smaller number, like 250,000 instead of 500,000 or whatever. When I was doing the tests in VirtualBox and so on, I used a fairly low number because I was rebooting every 45 seconds. As I was trying to figure out what's going on and debugging this. It's thousands and thousands of boots. So using a smaller number would definitely be faster. But yeah. Can't really see, but this machine is booting from GELI, and in a second we'll be done with boot FreeBSD. And there's no unencrypted partition. The only unencrypted code on this is the 90 kilobytes of GBDE ZFS boot. And it works with boot environments. Any other questions? Thank you.
Could you please take your picture?